Okay. All right. Who here has taken linear algebra? Okay, a few. Um, I'm trying to think. This is one of the things like when you work in math and CS long enough, you're like, oh, everybody knows matrices, when in fact, probably not. So we're going to be looking at something like this. Does this look familiar to anybody? Kind of, yeah. Okay. So that's what we're going to do. Um, so this is something called a matrix. The book says it was invented in the 1840s. I did some Googling and it says that's false. The let's see, let me put this on the screen. So this website, which is very small, says that it started in China around the 2nd century or the 4th century BC, which is very much not the 1840s. So that's always fun. But again, this is just, I Googled when were matrices invented, and this is the first site. So it is from St. Andrews. So I think it's probably reliable, but this is just one site. All right. So matrices are essentially two-dimensional arrays. So if you ever have like a list of lists, so let's say we have a list of 1, 2, 3, and 4, and then we have another list, 5, 6, 7, 8. This is a list of lists. This is a matrix. And so the way we write it in math terms is just we have rows 1, 2, 3, 4, 5, 6, 7, 8. And so we just take away those extra brackets. So yeah, once we get into LaTeX, I'll tell you how to write a matrix. Um, so in math mode, we'll have begin, and then the curly bracket, and then B matrix. And then let's say I have, so I had 1, 2, 3, 4, 1 and 2, 3 and 4. And again, we'll go over what this all means. This is your teaser for later of this is how in tech you'll write something like this. And so then it looks pretty and in math. Yeah.
Did a little bit more research. It says matrix, they put 1940s because it was named a matrix in 1950.
Okay,
Not from me.
I could see that. Yeah. So they said matrices when it actually called matrices. Okay, that makes sense. All right. So it's a rectangular array of numbers. There's no empty spaces. So something like this, if we erase 7, that's not a matrix. So we've got to have an entry in every spot. The plural is matrices. The singular is matrix. We'll see this again in graph theory where we have vertex and vertices. And so a matrix is going to have rows and columns. So this is going to be row 1. This is going to be row 2. This is column 1, column 2. Here, let's make it a different color so we don't. Column 1, column 2, column 3, column 4. This is the one place where we do start counting at 1. So unlike in a lot of computer science, we've got the first row in the matrix, the second row in the matrix. And so we typically write the rows in terms of M, the columns in terms of N. And so these are just letters. We could use any letters, but you'll typically see those if you go look up stuff online. We can say the size of a matrix is n m times n, and this is pronounced m by n. And so if I'm looking at like a 3 times 4 matrix, I'll say I'm looking at a 3 by 4 matrix. And so that tells me that it has 3 rows and 4 columns. Do we have any restrictions on M and N? Yeah.
They must be 0 or negative.
Right. They have to be positive integers. So sometimes you'll see like the Z with a plus, that's positive integers. So M and N are positive integers. It's a lot of like definitions today to get us all on the same page. So when we have a case, so this is a case where we have 3 rows, 4 columns. What if we had a 3 by 3 matrix? So when M is equal to N, we call it a square matrix, which kind of makes sense, right? A square is when it has equal length and width. And so if we've got an equal number of entries in the rows and the columns, then it's a square matrix. Additionally, each entry in our matrix gets its own address. So this is where, like, if we're looking at a 2D array where we can say like I and J, where that's how we like index our 2D array. Each entry also gets 2 numbers. And so we typically write it row, column. So row comes first, column comes second. And we'll typically use the letters I for rows and J's for columns. Again, these are just letters, so we could switch them if we wanted to and confuse everybody, or we could choose X and Y. They're just letters, but traditionally it's I and J. And we've got restrictions where so both of them have to be greater than or equal to 1, obviously. And so if I is looking at rows and we use M for the size of our row, then I has to be less than or equal to M. And then for J, if we use N to be the size of our columns, then we say that J also has to be less than or equal to N. And so let's look at an example. So if we have, let's say this matrix is called A, we've got A, 1, 1, A, 1, 2. A21 and A22. So let's see, row 1, column 1 is A11, and we kind of write it shorthand next. So like if we've got a little letter to represent that item in the matrix, we'll write the, so we've got I and J, we write it A, I, J, just right next to each other. No commas needed when we're doing this sort of shorthand. Row comes first, column comes second. Row comes first, column comes second. And this makes sense for a 2D array too, right? Like if I've got a list of lists, the first index that I give it is gonna, like if I have 0 or 1, that's gonna choose which one of the lists I'm looking at. So each one of these entries is gonna be its own row. So I'm gonna choose the row first, and then, so if I have 0 and then let's say 3, it's gonna choose this list first, and then it's gonna choose 0, 1, 2, 3, then it's gonna choose element 3, right? Row comes first, column comes second. I for row, J for column. The number of rows is M. The number of columns is N.
Question.
Yes,
For the thing of M and N,
yes.
would it be equal to M minus 1 for like syntax or like, like if you were to select something for a 2D array, it starts at 0.
Mhm.
Would putting it up to N give you something that's outside the list?
Correct. Right. So when we're working with arrays, our options here are 0 or 1, even though M is equal to 2. And for N, our options are 0, 1, 2, or 3, when N is equal to 4. Yeah. So we're shifting our counting by 1. So we start counting at 1 with matrices. Other questions? Great. Okay, let's do an example. See, 1, -4, 0, and -2, 0, 5, 7, and 1. So I would like to know what's M, what's N. Whoa, no, don't do that. Is it square? What's 1, 2? What's 2, 3? What's 2, 2? So think about it for a second. All right, the bell stopped ringing. What's M? How many rows are we working with? 2. How many columns? Is it square? Why not? Yeah, 2 is not 4. What's 1, 2? 1 comma 2? What's 2 comma 3? What's 2 comma 2? 5. Right. So row call I, J. So just to remind you, row comes first, column comes second. All right. Great job. So when we name a matrix, we typically name it with an uppercase letter. So you'll see like A, B, C, or D. M is also really common. I think you can guess why. And when we're talking about an individual element in one of these matrices, when we just have an idea of the matrix, that's when we use the shorthand. So like if we're talking about a specific element at row I, column J of matrix A, we say letter A, lowercase, and then in the subscript, we have I and J. So note when you go to type it on the computer, if you just do like A, I, J all next to each other, that's not the same as this. When we do it in LaTeX, we'll have A underscore curly brackets I, J. And so this is in math mode. Again, this is your teaser for when we actually talk about this. And so to make it actually look like a subscript, we'll do this. And so the underscore is what puts down below. So if we're talking about elements in matrix B, it'll be the same thing. What about in matrix M? Lowercase m. Right. Pattern recognition. So the book has this whole thing of, here, let me pull it up and show you instead. Do I have it? Oh, I do have it open. Great. So this is their generic matrix of we have m rows and n columns. And so the very first thing is A11, and then we go up to A1n. N is the number of columns. And then similarly, if we go down the rows, we get the last row starts with AM1. M is the number of rows until we get to the very last where we have AMN. So row M, column N, the very last thing in our matrix. So this matrix has what we call diagonals, or every matrix has diagonals. Not all of them are super pretty and symmetrical, but we've got diagonals. So here, this is kind of the self-explanatory part, where that's our diagonal. So we start at the top left and we say A11, A22, A33, A34, A44, up into AMN. What's I and what's J for a diagonal entry? What's our restriction on those? Yeah.
Or going on that main diagonal, they have to do the same.
Right, yeah. So we need I to equal J in order to get a diagonal entry. Okay. I'm going to move away from this. This is also in the textbook. So Aij, where I is equal to J. We call a diagonal matrix a matrix where the only entries are diagonals. So let's look at a 3 by 3. So something in 1, 1, that should be 2, 2. That should be 3, 3. And everything else is 0. That's a diagonal matrix. We say A is diagonal. So there's no restrictions. So this could be 23. This could be 42. This could be 999. Doesn't matter what those numbers actually are, just that everything else is 0. All right, we clear so far? Great. We can do math on matrices. So let's say we have 1, 2, 3, 4. Let's call that A. And we'll have B, which is 5, 6, 7, 8. We can do something like A plus B. And the way we do that is we'll look at each of the individual elements. So for A plus B, this is going to give us a matrix in and of itself. And for this first entry, we're going to add the first entry in A, the A11, 1, and we're going to add B11. So this is going to give us 1 plus 5. The A12 entry, the row 1, column 2 entry will be 2 plus 6. The row 2, column 1 entry is 3 plus 7. And the row 2, column 2 entry is 4 plus 8. Process of elimination. So we add those together, and then we get 6, 8, 10, and 12. And that's A plus B. We could also choose, so let's say if we have, we can do a scalar multiplication. Scalar here being just a number, that's different from multiplying two matrices together. That's a little bit more complicated. So if we do 3 times A, what that means is we just multiply 3 by every number in A. So that's 3 times 1, 3 times 2, 3 times 3, 3 times 4. So it applies to every number. We could do negative, if we just said negative A, what would that do? Multiply them all by -1. So we negate the matrix in that way. So that would give us -1, -2, -3, -4. You'll see this in some of the homework examples, where if you ask, like, if we do B minus A, that's secretly B plus -A, where we've negated everything in A, and then we add them together. Even though if we did B minus A now, you could be like, okay, 5 minus 1 and 6 minus 2. So there's a secret step in the middle that we kind of skip over and just do in our heads. Okay. Now let's look at the inner product. And so this is a case where if we are multiplying, okay, the book has all these numbers. I don't like those brackets. Let's redo that. So I don't like how the book numbered them. Um, but so I'm gonna redo it. So A11, A22, or no, nope, I'm getting my numbers mixed up. Sorry. A row 1, column 2. A row 1, column 3. A row 1, column N. And let's say we're multiplying that by some vector. So a vector is a matrix with only one row or only one column. So let's say B row 1, column 1, B row 2, column 1, B row 3, column 1, until B row M, column 1. So we want to multiply these two together. And so the way that we do that is this is what we call the inner product. And this is going to give us a number. And so the way that it works in my head is if we take B and here, let me see if I can actually do this. Duplicate. Maybe I can. Oh my gosh, I can. Yeah. So we take B, kind of flip it on its side, and then we multiply A11 times B11. We multiply A12 times B21, A13 times B31, A1N times BM1. So here, let's write this out. So it's A11 times B11 plus A12 times B21 plus A13 times B31 plus so on and so forth plus A1N times B. Let me give myself enough room here. A1N times BM1. So we do all those, then we add them all together, and then we get a number. Let's see an example. So let's say we're adding 1, 2, 3, 4, multiplied by a vector 5, 6, 7, 8. So that's going to be 1 times 5 plus 2 times 6 plus 3 times 7 plus 4 times 8. And I did this on my calculator beforehand, and this should give us 70. Is that part clear? So we take B, flip it on its side, multiply the vertical part, then add all those multiplications together. That gives us the inner product. Okay, we need to know that in order to be able to multiply matrices together. So for an actual product, we want to do something like multiply A times B. And so if we have, let's just do square matrices, 1, 2, 3, 4, and 5, 6, 7, 8. We want to be able to multiply these together. And so the way we do that is we do the inner product, where first we're going to look at this row and this column. And so the inner product of this row and column is going to give us 1 times 5 plus 2 times 7. That's 5 plus 14, which is 19. And so we're going to have a new matrix where we put that new number. And then we're going to move along to the next column. And we're going to say, now we're going to look at this row and this column. And so what's that? That's 1 times 6 plus 2 times 8. 6 plus 16 is 22. And we put that in our next spot in our new result matrix. Okay, we've gotten to the end of the columns in, so if this is A and this is B, we've gotten to the end of the columns in B. So that means it's time to move on to a new row. So we'll move on to row 2 of matrix A, and we'll reset to look at column 1 of matrix B. And we do the same thing again. So we ask, what is 3 times 5 plus 4 times 7? 3 times 5 is 15. 4 times 7 is 24. Fifteen plus 24 is 939. Someone tell me if that's wrong, please. So 39 goes here. And then you get the picture. We're going to look at the next row, the next column in B. And so that's 3 times 6 plus 4 times 8. 3 times 6 is 18. 4 times 8 is 32.
Small math there.
Yes, please.
13 plus 28 is 43, not 39. It should be 21.
Wait, is that supposed to be 28? Okay. What was that number again? 43. Okay. 18 and 32 is 3 plus 10. No. 15. Right. 3 and 1 is 4, plus another 1 is 5. Great. So now we have worked through all of our rows and worked through all of our columns. So the idea is, our algorithm is row 1 of A, and then for each column in B, here. For each row of A, let's call it I, for each column J and B, we do inner product of row I, column J, and that goes into the spot I, J, of our new matrix. That part's not in your textbook. This is just if you want an algorithm for how we did that. So we go through each row of A and each column. And so this is why for row 1, we did column 1, column 2. For row 2, we also did column 1, column 2. Questions? Yeah.
Like columns of-
Yeah. Okay, so let's say we have a, where's the note that I had on that? So let's say A is M by some number P, and B is P, some number P times N. These gotta match, and you will get, as a result, an M by N matrix. So there are some matrices that the shape is too different and you can't multiply. So for us, we just did a 2 by 2 matrix multiplied by a 2 by 2 matrix. The twos match, great. And so we got a 2 by 2 matrix as a result. Other questions? Okay. So let me double check. All right, so we've got a little bit of time. So let's look at example 9. This is on page 24. So it gives you the answers there. So maybe turn to your neighbor and work through this. So we've got two matrices. Compute the product. First do AB and then do BA. See what you get. Go for it. All right. So move this to a new page. So we know how to do A times B because this one's A and that one's B. So the question is, how do we do 1, 5, -2, and 6 with, oh, I see the problem. It's because it's not possible.
I would think.
Right. So if we try and do like 1 and 4, 5 and 1, and then 0 and what? Yeah, no. That's my bad. Okay, so let's take a look at the one we did before. So if A is 1, 2, 3, 4, and B is 5, 6, 7, 8. So we did 1, 2, 3, 4. We did A times B. So let's do B, which is 5, 6, 7, 8, and 1, 2, 3, and 4. So do that one instead. That's guaranteed to work. And I want to know, because like if I do 5 times 2, that's the same as 2 times 5. So it should give me the same thing. So check that. All right, 10 more seconds. Finish up all your multiplication. All right. Someone want to tell me what these numbers are? What's 1, 1? Just call it out. 23, 1, 2,
34.
34, you said?
Yes.
2, 1, 31, 2, 2,
Force.
46.
Don't trust me.
Are we in consensus? Did someone get different numbers? Great. All right, so 23, 34, 31, 46. As opposed to, oh, huh. Did we do something wrong? I don't think so. So what does this tell us? AB and BA, are they equal? No. So yeah, so this is one case where commutativity does not hold with matrices. Wait, is commutativity the right word? I think it is. Hold on, let me go back to the properties. Yeah, commutative is like A plus B is equal to B plus A. So commutativity does not hold for matrix products. What about A plus B and B plus A? What do we think? I mean, if we go back to where we added two matrices, we did A plus B. Is that the same as B plus A? I would think so, because addition is commutative, and so this would be 1 plus 5 versus we swapped them 5 plus 1, which is the same. So addition, so commutativity holds for matrix addition. What about A minus B and B minus A? I don't think so, because 1 minus 5 is different than 5 minus 1. So no. Great. Some more terms that the book has. I encourage you strongly, very strongly, to read through the textbook, especially in this section. So we have something called the identity matrix. This is a matrix where all of the things on the diagonal is 1. So 1, 1, 1. It's a diagonal matrix, but all of the entries on the diagonal are 1. On diagonal are 1. And so the identity matrix, we call it with a capital I and then either a lowercase n or lowercase m as the subscript. Typically, we see identity matrices, or I think they always have to be square. Yeah, they always do have to be square. And so either n or m works. So this is I3. But the reason why we say n and m is because we can have something like, let's say we have A, and A is, so the example in the book, A is 3 by 2. And so we can multiply this by an identity matrix of size 2. And so 3 by 2 multiplied with 2 by 2, that's allowed. And that gives us a 3 by 2 matrix back. And I'll let you look at the book example, but trust me that the answer, the thing that we get back is A. So that's why it's the identity, because we multiply A times the identity and we get A back. We could also multiply on the left. But here, where 3 by 2 on the right, we can't just swap them because 2 times 3 is not allowed. So we have to use a different size identity matrix in order for this to work out when we multiply I on the left. So we have to use I3. And that's going to give us A as well. It's going to give us a 3 by 2 matrix, which is the original size. Some other terms, inverse and invertible. So let's say we're multiplying A times B, and all of a sudden we find that we are getting the identity matrix. So whatever size it is. Then we found that B is the inverse of A. So we've multiplied these two together and we found that we get the identity. And then we can say that A is invertible. So there is a matrix B such that we can multiply A times B and get the identity matrix. Some things the books say that the reader should verify, and then I will also leave to the reader. So we write the inverse of A, we also call it A to the -1. That's how we denote that. A times its inverse is the identity, which is what this statement says. And also A inverse times A is also the identity. There's a thing in the book about how to find the inverse of A for a 2 by 2 matrix. That's pretty cool. And then we're kind of running out of time. But there's some properties here which are really important. So if we suppose that let's look at 3 matrices, A, B, C, and R and S are real numbers, then we look at the properties. So we have like closure, where M and N is the set of matrices. Specifically, N by N matrices. And so this is showing the same properties that we assume, these are the same properties that we assumed for integers and real numbers. So closure. So if we multiply or if we add or subtract two matrices, the result will also be a matrix. The commutative law, which is what we said for addition, that holds. The associative law, so A plus B, we add that first and then add C, that's the same as if we move the parentheses around. And similarly for multiplication. Note we're not changing the order here. We're doing A and B and then C, as opposed to B then C then A. It's still A, B, C on both sides. R is a real number, S is a real number, so this is doing scalar multiplication. And so this is also commutative. Distributive laws, we can distribute A in here. And again, the order here matters, especially for something like A plus B, then on the right we multiply C. So C gets multiplied on the right to both A and B. Then additive and multiplicative identities, 0 plus A is A. And then this is the identities that we talked about. Additive inverse, I hope is also clear that if I have 1, 2, 3, 4, there's some matrix that will give me 0, 0, 0, 0 if I subtract. And then similarly, if A is invertible, then there's some inverse that gives us, when we multiply them together, gives us the identity. So that's that property. There's additional properties talking about like the inverse of an inverse. And if we multiply two matrices together and find the inverse, then it's we flip the multiplication and find the inverse of both of them. So again, these properties are in your book. And the one thing we didn't talk about is transpose, which is we're basically just like flip it around. And I think with that, you can get started on the homework problems this weekend. They are, let's see, homework 2 has some in 2.2 and 2.3, so you should be able to tackle those at this point. All right, thank you, and I will see you on Monday.